Hello, in this video, let's discuss a question on DP on trees. Here is the question, read it and give it a try. You are given an integer n and directed a cyclic graph with n nodes labeled from 0 to n minus 1. This is represented by two DRA edges where edges of I is ui, comma vi, comma wi indicates directed edge from ui to vi with a weight of wi. You are also given two integers k and t. Your task is to determine the maximum possible sum of edge weights for any path such that the path contains exactly k edges, and also the total sum of edge paths is strictly less than t. Return the maximum possible sum of weights for such a path. If no such path exists, return minus 1. N is up to 300, the t is up to 600 where the maximum weight, and the number of edges is up to 300, and the graph is surely a DAG and there are no duplicate edges. For example, let's take this one, the first one. The k is 2, so it means that we have to select a path with exactly 2 edges, and t is equal to 4, so the whole weight must be less than 4. So simply we can select the whole graph, whole tree, 0 to 1, 1 to 2 with a weight of 3, and it satisfies both, so answer is 3. So coming to this one, coming to second example, let's discuss second one later. So for now, let's assume that there is no restriction on weight. So what if the question asks us to return the maximum weight possible for edges k? Like if the question is stating that we have to return the maximum sum of path consisting exactly k edges without any restriction on weight, then it is simple, right? Let's say we are at initially node 0, and what are the transitions and what are the edges that we can go through? So 0 is connected to this node and 0 is connected to this node also. And what will be the maximum weight that we can return from this? Let's assume that is, so we are at 0. So from this, what is our main goal? Our main goal is to return a weight with exactly k edges and also the maximum weight possible. So we are at 0, so we can think to take this edge, to consider 2, and then some answer that we can get from this one. So for now, let's assume we are assuming only the things that we can do at 0. We will not decide whether we select this edge or not, or we'll select this edge or not. So here we are at 0. So our concern is to only care about the nodes or edges that are incident from this node. The rest of the answer will be taken by that node, which is simply like a DFS. So there are two choices, two edges. So the first one is simply 2 plus function of node 1 comma 1. So we have to track the number of the node we are at and also the number of edges still now in the path. So only then we can get that whether the path we considered has edges k or not. Else how can we get? So function of node and the edges represents the maximum answer that is rooted at that node with that many number of edges. So this is the first possibility and this is the second possibility. We have only 2 edges here. So after getting these two, what will return? We will return maximum of this, maximum of 2 plus this one and 3 plus this one. And finally, what will be the base case, or when can we find the answer? If the edges is k, then we can get the answer, then return 0. If edge is more than k, then simply break the loop, return, and if edge is less than is equal to k, then we can store answer somewhere and we can get the maximum answer possible. But here there is some extra condition where sum is less than or equal to t, sum is strictly less than t. So how can we make sure that we are considering all the sum less than t? So that is also fairly simple, because the only condition is sum is less than t. So when we are trying to take an edge, what if we try to find the net edge weight, and if this is less than w, less than t, then we can add it, else we cannot add it. Is that very simple? So let's say we have this one. So let's say we have this, and what is the function now? So even now the function is the function of node and edge weight, and this returns the maximum weight that is possible. And before adding the weight, we will check whether that is less than t or not. If that is only less than t, then we'll add, else we will not add anything. That edge is useless, because if we consider the weight is becoming more than t, which is failing, so we'll consider that edge only if the sum is less than t. But will that work? So let's assume that this is the tree we have, and we are at 0. So we are at 0, and now we have the same graph. So we have 2 directing and we have 3 directing, and these are the 2 different subproblems we have. So let's assume that we are getting answer 4 from this somehow. Let's assume k is equal to 2, and also let's assume that there is no restriction on k now. Like for example, the two edges are considered here. So for now, let's check whether this will work or not. Not exactly the code. Let's check whether it will work or not. So let's assume that this is returning 4 and this is returning 0. This is returning 0. And this edge is 2 and this edge is 3. So from this, what will return? From this, we have to return the answer because this is the root node. So how can we, so what is the answer here? So if we select 2, then what will be the answer? If we select 2, the maximum answer will be 2 plus 4. Because 2 is the present edge we are selecting and 4 is the maximum answer that we are able to get from the subtree rooted at 1. And generally if we take this one, then what? Then 3 plus 0, right? Because from the node, from the subtree which is rooted at 2, the maximum edge, the maximum path sum we can get is 0. So if we select 3, this is the only path we get. And this is 6 and this is 3. So the question is saying that t is equal to 5. So the only path, the path should have some less than 4. But here it is greater than 4. It is greater than 5. Like it is greater than equal to 5. So simply ignore this. So we'll return 3. So the answer is 3. Is this correct? No. This is the maximum weight which is of length 2 and the sum is 4. Which is greater than 3 which we found. Which is this path. So from this we got that the approach is wrong. We cannot simply store function of node comma edges and we cannot simply return. Because the main thing here, so we can understand that the main thing is not only about return the maximum answer. It must be less than t. Like here we are returning only 4. But we are not taking care of 2. We are not taking care of 2. Why? Because this is not the maximum. But finally, we must take this to get the answer. So what are we doing now? So the thing we are doing wrong is we are greedily thinking that returning the maximum answer will give the correct answer. But here it is not the case. Because here we have 4 and 2. And we are returning 4, not 2. Why 4? Because this is the maximum weight. But there may be a possibility where adding this edge can be more than t. Can be more than or equal to t. And by taking 2, we can get less than t. Which we exactly want. So from this we got that greedy will absolutely fail. And the main thing now we want is to find whether a weight is possible or not. So here, what if we try to store some vector saying that the path with 2 is 1, the path with 4 is 1, then it is simple, right? Because if we are storing, then we can traverse all with weight 1 and then we can try to take something. The main thing here is we are not missing information about 2. Maybe the time complexity will increase or anything. We will try to optimize it. But for now, the thing which we are failing in the main approach, we are trying to get at least some idea. So here we are ignoring about 2. But we have to find an approach where 2 is not ignored. 2 should not be ignored. That may be a main thing later. So if we try to store something like this, something like vector where with edge weight we have to know whether that is 1 or not. So if that is 1, it means that the edge is there. Like there is a path with that weight. And coming to here, what to return here? Because in the before thing we simply assumed that we will return the maximum value. But here what we will return? So no need to return anything here. Because we are storing the information. So from a function, there can be two things. The first one is returning some answer. And the second one is storing in the answer. So that we can store in some global vector. And then this can be accessed for the future DPs or future DFS. So here we are going to choose the second one. Because there is nothing to return here. Because ideally we are updating the vector with 1 or 0. If there is a path, we'll update it as 1. If there is no path, we'll not do anything. So default it will be 0. So there is nothing to return here. And the main thing is just storing the information that there is a path with weight 2, there is a path with weight 4 as well. So now we can store DP of node X and edges. X is weight, let's assume X is weight. So we can store something like DP of node and the number of edges and the weight is equal to 1 if there is a path starting from node and with X weight and edges, like edges, number of edges and X weight is equal to 1 if there exists something like that. So here, and if it is 0, for example, let's assume the state is 0, it means that there is no edge possible, like there is no subtree or subgraph possible such that starting from node and having E edges and exactly weight X. If there is 0, this means that there is no possibility. So now it is simple, right? So at every node we can try to update the edges that we are able to get to 1, and then finally we can get the answer. And what is the size? What is the deep size GP? It will be 301 into 601 into 301. For example, let's say we have two edges with weight 301. Let's assume 301, 301, and then let's assume t is equal to 600. So if it is 600, do we anyways or anytime we want the information with respect to path with edge weight with the whole weight 602? Obviously no, because t is equal to 600. So why anyone will care, or why do we care about storing information which is greater than 600? We'll never care. So we can, in the DP we can try to store only till 601. Even though there may be a path with more than 600 weight, we will store only this because we only want information with only paths less than this weight. So we'll store something like this. So let's check the code for this. So firstly we are traversing through all the nodes and calling dfs of u comma 0 comma k. It means that the initial weight is 0, the node we are starting is u, and the number of edges we want is k. So how the dfs will look like? If s is greater than t, so if we reach the state with weight more than t, simply return, not return 0, so simply return, because we don't need to consider the rest graph because this is greater than t. So in the future also it will be greater than t, so simply return because we don't care about paths more than t. And now if the dp of this is not equal to 1, it means that it is already traversed, so no need to traverse again. So simply return, and then we reach this state. So if we reach this state, then what does this mean? It means that we have to make dp as 1 so that we are able to get a state with this path, with this configuration USD, because only then we reach it here. So make this as 1 and then start traverse through all the edges incident from that, and if the net weight is less than t, then call dfs of new node comma total weight, which is s plus w. The weight till now is s and the edge weight is w, so the net will be s plus w, and then the total number of left edges is d minus 1, because till now it is d and we have taken one edge, so the rest will be d minus 1. We want d minus 1. So if the d is 0, then we can return also. So if the d is also 0, then we can return. So this is just a rough idea of the code. We will check the correct code later. So hope you got this. Why we are storing extra d? Because if we simply try to return the maximum edge, maximum weight from every subtree, it is wrong because we don't have the complete information regarding the less weight paths also. So what is the time and space complexity for this? The time complexity is approximately 5e7, which is 300 into 600 into 300. And space complexity is not fine because space complexity is also 5e7, but we cannot store more than 1e6 size array in the most cases. So let's try to space optimize. This is very simple, right? So at a u, what are the transitions possible? So dp of u of w1 comma e, and that rises to a new path, new dp, where it is dp of v, weight 2 and e plus 1 or e minus 1, anything. So there is a state where exactly 1 is changing. So e is changing to e plus 1 in all the transitions. So if there are many edges, in all the edges, it will start from e and it will go to e plus 1. So it is very standard way to space optimize. So we can simply space optimize this and we can get both TC fine and space complexity fine. So with this, there is also another interesting way to solve this. Let's check that. So in the before approach, what we have done, in the before approach, we have tried to store dp of node edge weight, where we are storing all the weights to get whether a weight is there or not. So why we are storing all this? We are like in this, how can we find the answer finally? So in this finally, we can go through all the states. So the number of edges we want is k. So we will traverse for all the nodes and we will get if dp of node and k and then all the weights till less than t. So if any dp which is like this is equal to 1, it means that is possible. So we will take maximum weight possible. So we'll traverse through all the dp states with dp of node and dp of k with all the weights less than t. If that is 1, we'll maximize the answer. So we stored the information with respect to all the weights, because dp of node of edge weight. So for every node and edge, we are storing the information for every weight. For example, node 3 and weight edge 0, edge 1. So for this, there may be only few paths, where there may be only few graphs with edge weight, edge 1. So if we are having few states, then we'll have few weights also. But here what we are doing, we are storing the information with respect to all the weights. For example, if we are only having the paths with weight 1 and 2, we are storing that dp of 1 is equal to 1, dp of 2 is equal to 1, dp of 3 0, 4 0, 5 0, 6 0, and so on till 600 0, which is slightly better, right? Because we only want the information whether that is there or not here, but indirectly we are storing the user's information also, where dp of 3 is 1, dp of 3 is 0, dp of 600 is 0, but we ideally we don't need that. We only want the things which are there. So we only want dp of 1 is equal to 1, dp of 2 is equal to 1. So how can we get that? So simply we can store dp of node and edge as the weights possible. So here what will return? So dp of 3 comma 1 is simply the set of 1 comma 2, because we only care about individual, like we only care about unique weights, so 1 and 2, and we are using a set. So if this is the state, if this is the dp that we are writing, then also it is fine. Then we are directly trying to space optimize this also indirectly, right? So initially for any node, for example, let's assume this is the graph we have, and initially for every node there will be a set consisting of 0. It means that there are, like, we are considering no path initially, so the weight is 0. So for any node with edge count 0, there will be a set 0, indicating that there is no path with 0 edges starting from any node. So that is initially the dp we have. And what are the transitions and how can you find the answer? Let's say we are at node u, and there is a path, there is an edge with weight w, and we are reaching node v. So if this is the case, then what is dp of u of e? So dp of u of e indicates the set of weights that are possible, that are having exactly e edges and path ending at u, because we are thinking with respect to this. So ending at u with e exactly number of edges, and it contains set of weights possible. And now we are at u. So we are at u and we are having edge of w. So what the things will change? So what will care? So let's say we have value x which is present in dp of u of e. So let's assume that dp of u comma e is the set containing x. So is the set containing x. So if this is the case, then can we get any extra information about v? We can get yes. So here there is a path ending at this with a weight x. So what if we try to take the same path including this edge? So indirectly it means that we got a new path where, like, we got a new dp of v of e plus 1, right? Because till now the edges is e, we are considering this also. So the new thing we care about is dp of v of e plus 1, because ending at v and we have e plus 1 edges. And for this what we can do, we can add x plus w to the set of dp of v e plus 1. Why we are adding? Because indirectly, if we are having the path with x weight till u, we can consider this edge. Like, we will consider only if e plus 1 is less than k. So if this is less than k, then we can add dp of v of e plus 1 to this set. We can add x plus w weight, so that we are able to get this new kind of weight by considering the path ending at this. So we got the transition also. And what is the answer? The answer is maximum of all the weights possible in dp of any node and k, because we only want the path with k nodes, k edges. So simply traverse through all the possible nodes. So for I is equal to 0 node to I is equal to less than n node, we will traverse through sets of dp of node and k, and we will find the final answer. We will find the maximum answer. So hope you got this. Let's check the code for this. So initially so this is the main function. Please ignore the variable namings. We are just using the global variables, and then we are initializing the adjacency list and then find the adjacency list. So for every node, initialize using weight the node comma w, v comma w. So u to v is the edge with weight w, and now assign the dp. So initially the set is empty, like initially set is empty, so dp dot assign the size n vector with k plus 1. So this is simply like dp of n and k plus 1 as an empty set initially. So empty set, and now we discussed that we are going to add 0 for every set because there is no path. That means that weight is 0. So for all the nodes, dp of u of 0 dot insert 0, because for every node, for every path with 0 edges, add 0 weight. And now do dfs for all the possible nodes. And now what will dfs do? Dfs is also very simple. So if e is equal to k, it means that we reached k. So simply return, because for now we reached k. So if we consider any outgoing edge from this, it will become k plus 1, which is invalid. So we reached k, so simply return. Don't traverse dfs. Don't do dfs. And now go through all the possible all the possible weight paths that this state have. And what are those? It is simply dp of u of v. So we are traversing through set weights of dp of u of v. And so we are traversing and then traverse through all the edges. So for every weight, we are traversing every edge, because for every unique one, we can take that node and we can get many different number of weights for the next set of graph. So what will be the new set of weights? It will be simply s plus w, because s is still now, because dp of u of e is still now. So dp of u of e, s is still now. So till v, what will be the new weight? It will be simply s plus w. So dp of, so the new weight will be s plus w. If it is more than t, so if the new weight is more than t, simply continue, because we don't need to update that. And if this is less than t, then insert ns, the new weight, into the new dp state. So dp of v of e plus 1 dot insert ns, because we got a new path with this weight. And then simply do dfs for rest of the tree. In this way, we can do dfs. And then after doing dfs, we'll reach this path. We'll reach this, and then traverse all the nodes. And if the set dp of u of k is not empty, it means that there is some set with that state. If there is some set, then find the maximum answer. So in a set, what will be the maximum value? It will be the last value, which is simply dot r begin. So maximum of answer and star of dp of u dot r begin. It means that dp of u of k is the set of weights that are possible for this configuration, and we want a maximum, so dot r begin. We want the value, so simply dot star it. So we are getting the value, not the iterator. So in this way, we can find the answer simply. And we can space optimize this also, because dp of u of e is the set containing the edges, the weights for this path. And from u, what we'll update? We'll update dp of v of e plus 1, which similarly stores the weights. So e is changing to e plus 1. So we can simply space optimize this also. So what are the two ideas we discussed? So first idea is we can try to store dp of node and the number of edges and the weight. So if this is 1, it means that there is a path with this configuration. If there is 0, there is no path. And also, what is the second idea we got? So the second idea is dp of n of k is the set of edges, is the set of weights possible with that configuration directly. So indirectly we are storing, we are space optimizing indirectly. Let's check the main code again. So that is same as this, but for the before one, we can try to add a small optimization where, like in the code, what we are doing, in the code we are directly inserting into dp and then we are doing dfs. But what if there is ns already in the dp of v of e plus 1? It means that we are uselessly doing extra dfs. So before adding the new weight into dp, just find whether it is already there or not. If it is there, then don't do anything. If it is not there, then add this into set and do dfs. So before adding, simply find if it is there or not. So if it is not there, then insert this and then do DFS. In this way we can find the answer. If you have any doubts, comment below. See you in the next video.